All righty. I want to thank you for your patience from last time. Um, it was tough watching me having to sit where I was because they were tenting tenting the place where I normally do this lecture, and having to sit down and write on this little board and erase every few seconds and all of that. And then it was in the midst of the hardest theorem we've had all semester. And by the way, by far the hardest that we will have. The rest of the stuff after this is really easy. So we'll look forward to that. But we still have the rest of this theorem to prove, so please tighten your seatbelt. Please try to follow. Hang in there. You'll be able to follow everything after this, and you probably will be able to follow this even better than I do. But let's pray and let's kick off. Father, again, thank you so much for how you have led us together, how you have allowed me to teach for all these years at Biola, and how you've glorified yourself in many classes, in many, many students, and the lives that they've gone on to lead after leaving Biola. Father, I thank you for all of that, and I pray you'll continue to bless them, and you'll continue to bless the students in this class so that their careers in their Christian lives, their careers in their professions, their careers in mathematics, that they will all just be glorifying to you. And I pray that the remaining time in this class today will be glorifying to you in Jesus' name. Amen. Okay, we have been proving that if you're in a locally Euclidean space, when you hear locally Euclidean, hopefully it brings to mind the idea of a manifold. Okay, but you're in a locally Euclidean space, it's Hausdorff, and it's connected. So you don't have these two separate locally Euclidean spaces wandering around there. It's connected. Then the punchline is that the following three things are equivalent. The space is second countable, the space is paracompact, and the space has a compact exhaustion. And so we are in the process of proving that equivalence. We've already proved that if the space is paracompact, then it is second countable. We have already proved that, have we proved anything else? No, but we're in the process. That was the tough one. So now we're going to prove that if if it's second countable, then it has a compact exhaustion. So why don't I start over here? No use wasting a perfectly clean board. So 1 implies 3. For a countable base, and let's give that base a name, say script B, and it'll be equal to V sub I, these being integers because it's countable. We may assume that each V sub I has a compact closure. And of course, the notation that we're using for that is CL of V sub I. Because if it doesn't, I'll call this a for instance, but we're not doing an example. For instance, if not, we may weed out those V sub I that do not. Okay, since, and here's why we can do that. Since X is locally Euclidean, and Hausdorff, by the way, since it's locally Euclidean, every element of X has a neighborhood that is homeomorphic to an open ball in Rn. Which does have a compact closure. So now just pull back to X. From Rn, pull it back to X via that homeomorphism. Okay, so if you have one of the V sub i's that doesn't have a closure that's compact, then throw that away because there are plenty left over that do. All right. Now, since the V sub I is a countable set, we can put them in order. Okay, so V1, V2, etc. And let K1 be the closure of V1. It's not a very good C here. That is closure of V1. All right. Now using induction on N, you may have smelled that coming. Let I sub n be the smallest integer such that K sub n lives inside U1, V1, union V2, union, union, V sub n. V sub I sub n. It's the smallest integer such that K sub n lives inside that finite union up to that smallest integer. Okay? Let's see. That's not where I wanted to go. Yes, it is. Thank you for hanging in there. That's exactly where I wanted to go. I accidentally got it right. Then what do? We let K sub n plus 1 be the closure of this union. In each case. And that takes care of it. Okay, so 1 implies 3. Now, 3 implies 1. Well, since 3 is true, I know that I have a compact exhaustion. So consider a compact exhaustion, K sub I, consider a compact exhaustion the sets are, we'll call them K sub I, just to keep it uniform. And take a collection of open sets that are the interiors of these guys. So take the open sets, W sub I equal to the interior. That's what that little circle means, if you remember. It's the largest open set inside K sub I, the interior of it, okay? Then, what's true about the closure of W sub I? The closure of W sub I is still inside K sub I. Why? Because the closure is the smallest. It's the intersection of all the closed sets that contain W sub I. And this is one of the closed sets that contains W sub I. So that means that, that it's contained inside K sub I. Okay. Very hard to stay on stay on the right line here. And this is what this looks like. It's really a mess. Okay, it's neat, but it's pardon the pun, it's compact. So the closure of W sub I lives inside the compact set K sub I, and the closure of W sub I is compact, therefore, for all I. Okay. And I'll say now, the W sub i's form an open cover of X. And they have that special property that the closure of one, so the closure of W sub I, lives inside W sub I plus 1. So they're telescoping. Okay? Now, this next statement is going to be, even though it's trivial to say, it's going to be outstandingly important in a little while. So, fix an open cover. We'll call it U sub alpha. For X. Now, if you'll let me take time out for a moment, I'll be right back. Thank you for giving me a little bit of time, but of course it didn't take much time for you. I do need to make one correction. To complete the cycle of equivalences, I don't need the 3 implies 1. I need the 3 implies 2, because we started off with 2 implies 1, and 1 implies 3, and now 3 implies 2. That finishes off the equivalences. So this is going to make a lot more sense. Okay? All right, so here's where we are. Fix an open cover for X, column U sub alpha. And let X, little x, be an element of big X. Okay? Then there exists, the same kind of trick we pulled before, there exists a smallest integer and I think this time I just call it I, yeah, such that X lives in W sub I, but X does not live in W sub I minus 1. Okay, so you can pull out an element that lives in the higher one that doesn't live in the lower one. And let's take a look at this complement, the closure of W sub I slash W sub I minus 1 is a compact set. right? It is a closed subset of a Hausdorff space. It's a compact set. And, okay, so enough said. That's compact. Now, suppose that I is greater than or equal to 3 for no apparent reason except I asked you to. If I is greater than or equal to 3, this compact set is covered by the open sets, and I'm going to call them V sub alpha comma I. I is greater than or equal to 3. V sub alpha comma I is equal to U sub alpha from our open cover intersect W sub I plus 1 intersect the complement, let's build this a little at a time, of the closure of Wi minus 2. So U sub alpha intersect W sub I plus 1 intersect the complement of the closure of W sub I minus 2. And hopefully the people are all saying, huh? I want to show you why this works. Which means I'm going to draw you a pretty picture. I don't usually draw pretty pictures. But this time, it really helped me see it. The picture is not the proof, obviously, but the picture is really going to help. So let's suppose that I is 3, okay? So let's see, now where did all this start? K sub I, that started with 1. So let's start with, here's K sub 1, and I'm giving it a solid border because it's a compact set. But inside K sub 1 is W1, which I'm giving an open boundary, and that lives inside the closure. In fact, that lives inside K sub 2. Let's see, do I want K sub 2 there? I think I want W sub 2 here. Okay. And K sub 2, let me make sure. No, this is, let's see, yes, I'm doing it exactly right. It's always comforting when that happens. Okay, K sub 2 lives inside W sub 3, which of course lives inside its closure. It lives inside K sub 3. We're going to do this one more time. So this lives inside W4. Which of course lives inside K4. All right. Now this goes on, of course, but this is all of the picture that I need, because then you can restart it for different values of I. Now, here's what I want to do. for I equals 3, this is the closure of W sub 3 slash W sub 2. Okay? And I want to show that that's covered by W sub 4 intersect the complement of the closure of W sub 1. So that's my goal. First goal is to pick up my glasses so I don't step on them. My second goal is to pick up my pen because I'm having to balance everything here. But I'm going to do this in color so that hopefully it'll help you as much as it did me. The blue is going to represent W sub 4 intersect the closure, the complement of the closure of W sub 1. So that's this guy with I equals 3, okay? And so let's see if I can do this accurately. W sub 4 is this last dotted line, so I've got to stay inside that, but I have to stay outside the closure of W1 which I'm going to put inside here. So K sub 1 is what it was before, the one with the black line, but W sub 1 is going to be the blue line, okay? Now what is the closure of W sub 1? Well, that's this black line. So I've got to stay outside of that and stop at this dotted line. Trust me, this little Venn diagram really helped me see this. Okay. The blue is W sub 4 intersect the complement of the closure of W1, and the closure of W1 is this solid box here. So the blue is that intersection, okay? Now, in red, we're going to do what's supposed to cover it. So that would be, I'm sorry, in blue is what's supposed to cover it. In red is going to be what's being covered, the closure of W sub 3 slash W sub 2. Okay. So, where's the closure of W3? Well, W3 is this little open space in here, so its closure goes to this solid black line. But where am I going to have to stop? I have to stop at W2, which is this dotted line. So I've got to stop right there. And now my question is a simple one. Is everything that is in red inside what is in blue? So hopefully you can see that well enough and study it. Everything that is in red is inside the blue, which means, now, notice that everything is intersecting all of the U sub alphas, and I can't do that because the U sub alphas are millions of little open sets and all that cover it. But as far as that intersection is concerned, I get that the blue covers the red, which is all that I wanted to show. So that means that the compact set closure of Wi, now you can take I to continue, of course. You can take this to be K sub 2 and K sub 3 and K sub 17, and then, then the next one is W sub 17, and then the next one's K sub 18, and you can continue that. So this just shows from the first one. I want to leave that here now, so that you can relish in it and its beauty. And now I'm going to erase the board. The thing that takes the most time in this one theorem is making sure that I'm in the right line in my notes. All right. Now, we're going to define a new cover. We're going to go back to that ram's head again. Script V sub I is going to be a subcollection of, you remember our little V sub alphas sub comma I, and V sub I, let it be a finite subcover a subcover for what? Where's my compact set? For W sub I closure, we've been calling it CL. Slash W sub I minus 1, it's closed, it's a compact set. So that finite subcover is guaranteed by compactness of this set. Okay, good. But that is for I greater than or equal to 3. So we want to take care of I equal 1 and 2. We're going to take care of that in a pretty synthetic way. If I equals 1 or 2, let V sub alpha comma I equal U sub alpha, U sub alpha intersect, and we'll just intersect them with W3 and let them both equal that. Okay, if it's covered once and covered twice, doesn't make any difference. Now, but here's what does make a difference. The collection of these open sets covers the closure of W sub I. Okay, that's what it's designed to do. So we choose a finite subcover. So that's what we're talking about here. So I'm being a little redundant here just to make sure that you get it. So choose the finite subcover, script v sub I, and we claim that the union of those from I greater than or equal to 1 now of the script v sub I is our, now what did we need? A little hard to keep track, but we are in the process of proving that 3 implies 2. I hope I said that right before. We're proving that 3 implies 2. Yes, I did say it right. So what are we looking for? We started with a compact exhaustion, and we had to find, we're trying to prove that the space is paracompact, so we had to find a locally finite refinement. We claim that this is it. That still has to be proven. But there's not a lot to it. It certainly is a refinement. Since, by design, we had these things inside the U sub alphas. And this is a finite subcover of these, so that's still inside the U sub alphas. So it is a refinement since each V sub alpha comma I lives inside U sub alpha for all I. So that part's easy. And for all alpha too. Why is it locally finite? That's the last question to answer. Well, the definition, may take everything back to the definition. So for all x in the space, such that x is in W sub I slash W sub I minus 1, we can take our required open set. Now, let's review what open set was required in the definition of a having a locally finite refinement. It was for every x, there exists some open neighborhood, we'll call it U, of x, with the property that U intersects only a finite number of that refinement. That's the definition of paracompact. That's what we have to show. So we can take our required open set, I don't need a comma there, to be U equals Wi slash the closure of Wi minus 2. Now remember, this is not, this should not be for all I, this should just be for all alpha, because I is chosen. I is chosen, it's the smallest integer such that blah, blah, blah. Okay, so that's chosen. So U is equal to this set, and it's exactly that set. By construction, only elements of script V sub I plus 1 script v sub I and script v sub I minus 1 intersect U. That's why we went through all that rigmarole before. This was for all I, by the way. My apologies for all I. And all these collections are finite. There are 3 of them. And the script v sub I cover X. That's where I started with. It was a refinement of a cover. It actually covers X. And so we have shown that any open cover U sub alpha admits a locally finite refinement. And that, as they say, is that. So, toughest theorem of the semester, but I thought it was important because this is intimately involved with differential geometry, with topological manifolds. And so I did want to show you that connection. But now we're going to go back, we're going to spend the rest of our time talking about pure topology. Topology. Time for me to get a drink. Okay, now hopefully you have lived long enough with this drawing that you don't mind saying goodbye to it. So let's say goodbye to it. I want to take a reasonable amount of time. I told you I was going to do this. And take a look at some properties that are related to compactness. Compactness itself, local compactness, paracompactness. There's just a tremendous myriad of weakenings of compactness. There's sequential compactness. There's countable compactness. There's Lindelof. There's a lot of these different ones. And I want to pick on some of them and show how they compare with compactness and how they differ from compactness. Okay. What do we know about compact sets? We know that, first of all, a closed subset of a compact space is compact. Okay. We know that a compact subspace now, wouldn't it be nice if we could say, since a closed subset of a compact space is compact, wouldn't it be nice if we could say a compact subspace of a closed set is compact, is closed? You can't. But a compact subspace of a Hausdorff space is closed. Part C, we know that the product, the Cartesian product of any number of compact spaces is compact. Now, when did you see that? You saw that in first semester. And this is a theorem that's due to another Russian mathematician named Tikhonov. Tikhonov's theorem says any Cartesian product, whether there are two or any finite number or a countable number or an uncountable number, any product at all of compact spaces is a compact space. Think about that for a second. Do you ever wonder where mathematicians got the ideas that they got? Now, I understand how they could have come up with the idea of compact because they probably explored properties of the real numbers, and closed and bounded in the real numbers is equivalent to compact. In fact, in all of Rn, it's equivalent to compact. But how did they think of the fact that if I take uncountably infinite many of those compact spaces, and I take the Cartesian product of them, I still can cover every cover with a finite subcover? If that doesn't blow your mind, and we proved it last semester in Topology 1, but if that doesn't blow your mind is, you got to blast. You've got to do something, because that's astounding to me. But verily it is true, and we proved it last semester. So a product of any number of compact spaces is compact. Part D. The continuous image of a compact space is compact. There are many more. Those are the four that we're going to take a real interest in now. We're going to start with what is probably the most natural one. If compact means that every open cover has a finite subcover, then why don't we allow it to extend a little bit and say, all right, what if every open cover has a countably infinite subcover? That's Lindelof. So you recall that that's the definition of a Lindelof space, that every open cover has a countable subcover. Okay? So Lindelof. What about A? Is it true that a closed subset of a Lindelof space is Lindelof? And the answer is yes. A closed subset of a Lindelof space is itself Lindelof. So in that way, Lindelof is similar to compactness. And here's the proof. Now, where is the theorem forcing you to start? Let A be a closed subset of a Lindelof space. So let A subset of X, a Lindelof space, also be Lindelof. No. That'd be nice if we started with what we wanted to prove. Also be closed. All we know about A is that it's closed. X is Lindelof. Okay? Now, what does it mean? Where is the theorem forcing us to go? What does it mean? If I wanted to show that A is Lindelof, I have to show that every open cover of A has a countable subcover. Maybe you're already starting to formulate the proof in your mind. If you are, it's a sure sign of drug abuse. No, that's not true. That's not true. Okay, but that's where the proof is forcing us to go. So let's say use of the script use of A be an open cover for A. Okay? Now, let's be precise. Then for, where did I put the alpha? Up on top. Use of alpha A, elements of script use of A, the union of the U alpha A's is equal to A. Okay? Or at least covers A. Now, let's take a look at each open set. Each U alpha A is equal to, this is by the definition of the subspace topology. Where A is a subspace of X. So in the subspace topology, what does an open set look like? It looks like A intersect an open set in X. Okay. Now, there's no reason at all why the use of alphas should cover X. They probably don't. But A is closed. So X slash A is open. Well, since X slash A is open, I can toss that into my open cover, and that's exactly what I'm going to do here. This is actually a pretty common construction in topology. When you have a closed set, you can take its complement and dump it into an open cover. Take its complement, yeah, and dump that into an open cover. So that's what we're going to do. Therefore, now I have use of A, I have these use of alphas, and so let's define U, script U, to be the collection of all the use of alphas, these that are open in X, and X slash A for all alphas. Then U does cover X, because this stuff, its intersections with A cover A, and this stuff, this is only one set, it covers everything else besides A. So U covers X. Okay, but X is Lindelof. So there exists a countable subcover. And what did I call this guy? Oh, of course, the ram's horn, script V. Thus, now I want a countable subcover of my open cover for A, and I'm sure you can smell this coming. The set script V sub A, which is equal to the intersections of all of this. So V let's see. I'll use a different index. V sub beta intersect A such that V sub beta is in script V, which remember is countable. Is a countable subcover for A, specifically for U sub A. And that's the end of the proof. So, a closed subset of a Lindelof space is itself a Lindelof subspace. What about property B? Property B is it true that a Lindelof subspace of a Hausdorff space is closed? And the answer is no, and it's trivial to prove. Praise God. B is false for Lindelof. And that's easy. So a Lindelof subspace of a T2 space is not necessarily closed. Now, why is that? Pretty easy. In the real numbers, is the real numbers a Lindelof space? Yep. Is it a Hausdorff space? Yep. So 0, 1 is clearly Lindelof. But just as clearly, it is not closed. So B goes out the window. What about C? What would C say? The product of any number of Lindelof spaces is Lindelof. And the answer, once again, is no, it's not true. Counterexample. So C is false. Now, how false is it? You might think, well, Lindelof has to do with countable subcoverings, so you might have to take out uncountable products. Now, even if you have the product of two Lindelof spaces is not necessarily a Lindelof space. And this example is a really famous example. So stay tuned, because this is actually an example of a number of things. So this is just the beginning. The product of even two Lindelof spaces need not be Lindelof. And this is so much fun doing this example. Here's our example. Consider the real numbers with the half-open interval topology having as a base, now a base for the usual topology in R is a collection of all the open intervals. But this one is half open interval topology, so it has as a base the right half open intervals. So closed at the left endpoint, and open at the right endpoint. Now, you should probably go through and check to prove to yourself that that is indeed a topological space for R, but it is indeed. And that's going to be our basis. Okay? And now, from basis to erasis. First of all, R with this topology is Lindelof. That R with the double line, the real numbers, with this topology is indeed a Lindelof space. And that deserves proof. Where's the proof forcing us to start? Let U be an open cover for R. Okay. Let's be specific though with this topology. Call this set, which is R, call it now S. So S is R with the half open interval topology, okay? Now, let T be the union of Euclidean open intervals with the property that their half open counterparts are in U. And here's what we claim. We claim that, we're calling it S slash T is a countable set. That has to be proven. We'll do it by contradiction. For if it were uncountable, then, now your knowledge of accumulation points and the like is useful here. Then, let's see. Since it's uncountable, then it has a two-sided limit point. We're going to call that P. Okay, well, what's the limit point? Every neighborhood of that limit point intersects the set in question. Okay, in a place other than P. Therefore, every open neighborhood of P in the usual topology now, open in the usual topology, contains points of S slash T. and it contains points of it on both sides of P. So that means that it's a two-sided limit point. Okay. Now, let's choose some base open set that contains P. Now the open interval from A to B is in T. That's how we defined T. Thus, that open interval can't contain a point in S slash T. It can't be in T and in the complement of T at the same time. Okay. But A intersect B must intersect S slash T, and that contain a point in S slash T. So that gives us our contradiction. Okay, now we're half done. All right, we're done showing that the real numbers with the half open interval topology is indeed a Lindelof space. Okay. And by the way, what was the punchline to this? So S slash T is countable. That's what we needed. Okay? Now, that's not quite what we needed. There's more that we needed. Sorry for the bait and switch, but we're almost done showing that S is Lindelof. Since T is an open set, so since T is usual topology open, and of course that's because it's the union of a bunch of open intervals. So I'll leave the cliffhanger here for you for a moment while I erase the other side. Since T is usual topology open, there exist countably many of these little guys in U such that the union of all of those, the union of all such, and the open sets now, C, D, covers T. So certainly the union of the closed intervals CD covers T because this is bigger. I'm including an extra point. Now, take countably many. S, let's see. Take countably many such CDs that cover the other part. So similar to what we did before. Now, why are there countably many that cover the other part? Because S/T is a countable set. So it's easy to cover that with countable sets. And combine the two subcovers to get a countable subcover for S. Therefore, S is Lindelof. Now we're done. Okay, so S is Lindelof. Now, where did we start? We started by saying that the product of two Lindelof spaces is not necessarily a Lindelof space. And all we've done so far is to show that the real numbers with the half open interval topology is a Lindelof space. But here's what we're going to start off by showing next time. Its product with itself, S cross S, fails to be Lindelof. So that's where we're going next time, and it's a little bit of a construction, and it's kind of a fun construction. So we're going to start with that next time, and hopefully that cliffhanger will keep you on the edge of your seat. You probably won't even be able to go have dinner or breakfast. You'll just be sitting there next class time, waiting on Friday to see what this construction is. God bless you guys. Stay smart, and I'll be visible again, Lord willing, on Friday. Goodbye.